In episode 104, titled Optimizers, SGD, Momentum, Atom, RMSprop, and Practical Differences, we focus on a practical truth about training neural networks. The optimizer you choose is less about elegance and more about whether learning converges reliably under your constraints.
An optimizer controls how the model updates weights in response to gradients, and small differences in update rules can produce large differences in training stability, speed, and sensitivity to hyperparameters. On the exam, you are expected to recognize the common optimizers, what problem each one is trying to solve, and why certain choices are common in modern deep learning workflows.
The goal is not to treat optimizers as magic performance buttons, but to treat them as engineering tools for stability and efficiency.
If you can diagnose whether training is slow, divergent, or oscillatory, you can usually reason about whether the issue is learning rate, noise, or curvature, and which optimizer behavior helps.
This episode builds that intuition so optimizer choice becomes a disciplined decision rather than a habit.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Stochastic gradient descent, abbreviated as SGD, is the basic approach of updating weights using the gradient estimated from a batch of data. You compute gradients for the current mini-batch, then adjust weights in the direction that reduces the loss, scaled by a learning rate. The word stochastic reflects the fact that the gradient is not computed on the full dataset each step, so it contains sampling noise that depends on batch size and data variation. That noise is not always bad because it can help the optimizer explore and avoid settling into brittle solutions, but it can also make training bouncy and slow to settle. SGD is conceptually simple, which is part of its value, because it gives you a predictable baseline behavior that is easy to reason about. The main sensitivity is the learning rate, because a learning rate that is too high causes divergence, and a learning rate that is too low makes training crawl. Understanding SGD as take a noisy gradient step sets the foundation for the improvements introduced by other optimizers. Momentum is a modification that carries past direction forward to smooth noisy updates and accelerate progress along consistent gradients. Instead of moving purely based on the current batch's gradient, momentum keeps a running velocity, which is a weighted accumulation of recent gradients. When gradients point consistently in a similar direction across steps, momentum builds speed and helps the optimizer move faster through flat or gently sloped regions. When gradients fluctuate due to noise, momentum dampens the zigzag motion, producing smoother trajectories and reducing oscillations. This is particularly helpful in loss surfaces that have narrow valleys, where pure SGD might bounce side to side while making slow forward progress. Momentum, therefore, improves efficiency without changing the basic idea of gradient descent, because it still follows gradients but does so with a memory of recent history. At a conceptual level, momentum turns noisy steps into smoothed steps with inertia, which often makes training more stable and faster. Atom, which is short for adaptive moment estimation, combines adaptive learning rates with momentum-like behavior, making it one of the most commonly used optimizers in deep learning. Atom maintains running estimates of both the average gradient direction and the average squared gradient magnitude, effectively tracking a first moment and a second moment of the gradients. The first moment behaves like momentum, smoothing gradient direction over time, while the second moment supports per-parameter adaptive step sizes based on how large gradients have been recently. Parameters with consistently large gradients get smaller effective step sizes, while parameters with smaller gradients get relatively larger step sizes, which can help balance learning across layers and features. This adaptivity often makes ADAM converge faster early in training, especially in deep networks where gradients can vary widely in scale across parameters. The practical appeal is that ADAM can work well with less tuning effort than plain SGD, though learning rate still matters. At exam level, you can summarize ADAM as momentum plus adaptive scaling that makes learning more robust across parameters. RMSprop is another adaptive optimizer that adjusts learning rates based on recent gradient magnitudes, and it can be viewed as focusing on the second moment behavior. RMSprop maintains a moving average of squared gradients and uses it to scale updates, reducing step sizes for parameters with large recent gradients and increasing them for parameters with small gradients. This helps stabilize training when gradients vary in magnitude across parameters, a common issue in deep networks and in recurrent settings. RMSprop does not include momentum in the same integrated way as ADAM, though momentum can be added in some variants, and the core idea remains adaptive scaling by recent gradient energy. The practical effect is often improved stability compared to plain SGD, especially when learning rates are difficult to tune globally. In many workflows, ADAM is more commonly referenced today, but RMSprop remains conceptually important because it illustrates the adaptive learning rate approach. For the exam, remembering that RMSprop adapts to gradient magnitude is usually sufficient. SGD with momentum remains a strong baseline because it is predictable, often generalizes well, and gives you a direct handle on learning behavior through learning rate and momentum strength. Many practitioners like SGD with momentum when they want a training process that is easy to reason about and when they are willing to tune learning rate schedules carefully. It can be especially appealing when the goal is robust final performance rather than the fastest early progress, because it often produces stable improvements when tuned properly. The combination of simple gradient steps and smoothing inertia yields behavior that is less sensitive to per-parameter scaling quirks than plain SGD, while still avoiding some of the complexity of fully adaptive methods. In exam language, it is fair to describe SGD with momentum as a reliable workhorse that provides strong baseline performance. The point is not that it is always best, but that it is a well-understood choice with consistent behavior. When you need predictability and can support tuning, SGD with momentum is a defensible default. ADAM is often chosen for faster convergence on many deep learning tasks because its adaptive step sizes help the model make progress even when gradient scales differ across layers. In practical training, especially early in optimization, some parameters need larger steps to start learning meaningful features, while others need smaller steps to avoid instability. ADAM's adaptivity often handles this automatically, which is why it is common in workflows where you need quick progress and where you might not have the budget to tune learning rate schedules deeply. That speed advantage is particularly valuable in complex architectures and unstructured data problems where training can be expensive and iteration speed matters. However, ADAM is not a free win because you still must monitor validation performance and ensure the optimizer is not producing overly confident or poorly generalizing solutions. The exam expectation is to recognize ADAM as a frequent default for deep learning because it is robust and often converges quickly. The mature perspective is that ADAM is chosen for efficiency and stability rather than for guaranteed superior final performance. Optimizer choice often affects stability more than final ceiling, meaning the biggest benefit may be that training succeeds consistently rather than that the absolute best validation score increases dramatically. If training is unstable, oscillatory, or divergent, a change in optimizer can be the difference between a model that learns and a model that fails. Once training is stable and the model reaches a reasonable solution, differences in final performance can be smaller and may depend more on data, architecture, regularization, and learning rate schedules than on optimizer brand. This is why experienced practitioners treat optimizers as tools to get reliable convergence, not as guarantees of the best possible accuracy. The ceiling is shaped by representation capacity and signal quality, while the optimizer shapes whether you can reach that ceiling efficiently and consistently. In operational terms, a slightly lower ceiling may be acceptable if the training process is robust and reproducible. This perspective also aligns with exam-style reasoning because it frames optimizers as practical engineering choices rather than as performance myths. Diagnosing training issues helps you decide whether the optimizer or its settings need attention. Slow learning can mean the learning rate is too low, the batch size is too large, gradients are vanishing, or the optimizer is being too conservative in its step sizes. Divergence, where loss explodes or becomes unstable, often indicates learning rate too high, exploding gradients, or an optimizer configuration that is too aggressive for the current model and data scale. Oscillations, where loss decreases then repeatedly spikes or bounces, often suggest that updates are overshooting, which can be helped by lowering learning rate or by using momentum to smooth noise. Adaptive optimizers can reduce sensitivity to gradient scale issues, but they can still diverge if learning rate is too high or if data pipelines introduce unstable signals. The point is that optimizer diagnosis starts with observing training curves and connecting patterns to update dynamics. When you can describe what you see and what it implies, optimizer choice becomes a reasoned adjustment rather than a guess.
Learning rate is the first knob to tune because it controls the step size and dominates training behavior across all these optimizers.
Even the most sophisticated optimizer can fail with a poorly chosen learning rate, and a simple optimizer can perform well with a well-chosen learning rate.
After learning rate, you adjust other settings such as momentum strength or adaptive decay parameters only if needed to address specific stability issues. This order matters because changing many settings at once makes it hard to know what fixed the problem or what caused a new issue.
In applied workflows, learning rate schedules and warm-ups are often used to manage early training instability and later convergence, but the core idea remains that step size control is central.
The exam expects you to prioritize learning rate as the main tuning lever because it reflects the practical hierarchy of influence.
If you get learning rate wrong, the rest rarely matters.
Comparing optimizers requires equal training budgets and consistent evaluation, because otherwise you are comparing different experiments rather than different update rules. An optimizer that appears better after a short training run might simply be faster early, while another might catch up or surpass it with more iterations. Differences in batch size, learning rate schedules, early stopping criteria, or data ordering can also create unfair comparisons. The discipline is to hold constant as much as possible and compare under the same conditions, including the same number of epochs or the same compute budget and the same validation procedure. This is the same methodological principle you apply when comparing any model choices, because you want differences to reflect the factor you changed, not accidental variations. Without fair comparison, optimizer debates become anecdotal and unproductive. The exam rewards the ability to recognize that fairness in comparison is part of sound machine learning practice.
Communicating optimizer choice should emphasize efficiency and stability trade-offs because that is usually what stakeholders care about in operational settings.
If the training process must be reproducible and robust, you may prefer an optimizer that converges reliably, even if it is slightly slower.
If iteration speed is critical and you need rapid experimentation, you may prefer an adaptive optimizer that reaches good performance quickly.
Stakeholders also care about compute cost because training time and hardware needs translate into budget.
Explaining that the optimizer controls how the model learns, not what the model can represent, helps clarify why changing optimizers is not the same as changing architectures or feature sets.
It also helps set expectations, because an optimizer can fix instability, but cannot manufacture signal that is not present in data. A clear communication framing is that optimizer choice is an engineering decision about reaching good solutions efficiently and consistently.
The anchor memory for episode 104 is that SGD is simple, momentum smooths, atom adapts, and RMSprop adapts. SGD provides the basic noisy gradient step behavior. Momentum adds inertia that smooths noise and accelerates movement along consistent directions. Atom adds adaptive learning rates and momentum like smoothing, often improving early convergence robustness. RMSprop adapts step sizes based on recent gradient magnitudes, supporting stability when gradient scales vary across parameters. This anchor gives you a quick recall map for what each optimizer is trying to accomplish. It also helps you avoid overclaiming differences because the family resemblance is clear. They all follow gradients, but they adjust step sizing and smoothing differently. When you remember this, you can answer exam questions about optimizer roles and selection without drifting into unnecessary detail. To conclude episode 104, titled Optimizers, SGD, Momentum, Atom, RMSprop, and Practical Differences, pick an optimizer for one case and justify your choice in terms of stability and constraints. If you are training a deep network on unstructured data where you need fast, reliable convergence to iterate quickly, Atom is a defensible choice because its adaptive step sizes and momentum-like behavior often produce stable progress with less tuning effort. If you are training a more controlled model and you want a strong, predictable baseline that often generalizes well when tuned carefully, SGD with momentum is a defensible choice because it smooths noisy updates while keeping behavior easy to reason about. In either case, you would tune learning rate first and monitor training and validation curves to confirm stability and avoid overfitting. This justification shows you understand optimizer choice as a trade between efficiency and reliability, rather than as a claim that one optimizer is universally best. When you can connect the optimizer to the training environment and goals, you demonstrate the practical understanding the exam is designed to test. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.